I don't know how long you're planning to talk, but
4 hours.
4 hours. Okay.
Yeah.
So see you tomorrow. And with that, Thomas.
Yeah, so thanks everyone for coming. And thanks very much to Lynn Clark and to Schneidereit from Mozilla. So I contacted you on Twitter and just asking, is there some random time when you're in Germany? And she said, oh, I will be there next Saturday for the next 6 months.
Not quite that long, but yes.
So yeah, and luckily she's located in Berlin at the moment, and they found the time to come to Munich to our meetup. So thank you very much. Big round of applause. So just a quick introduction. So last time we saw that there are some strange use cases already for WebAssembly, like running Windows 2000 in the browser.
You can even use the browser there. Surf the internet.
Yeah, so for those that missed, last time we set Internet Explorer 5 as the default browser inside the Google Chrome tab. And essentially, I think this is a good key quote for your talk. So just a few weeks ago, or a few months ago, one of the founders of Docker said if WebAssembly would have existed when they created Docker, they wouldn't have invented Docker, which kind of triggers some thoughts. So what is WebAssembly actually? What does it have to do with Docker? For those that are new to the technology, it's not just for the web. So we'll hear a lot from Lynn. And actually, so there's a new trend based on this WASI proposal that we now have different runtimes that actually can run WebAssembly without the browser. So they all, I think, are compliant to the WASI standard. And so there's some companies like Fastly, they also allow you to run WebAssembly now as cloud functions. So which is kind of the web still, but from the other side. And we're getting a package manager. So
It's really more of a WASM FTP or FTP server.
yeah, so at the moment it's just more of an inspiration, I would say. Yeah. So you cannot even reset your password or anything, but a lot of names are already taken. So this I hand it over to Lynn and Till. So Lynn and Till are both from Mozilla, as you know, and they're working both on the Rust and WebAssembly technology. So I think you could introduce better how I can what exactly is the structure and the roles you play in this game.
Yeah,
Thank you.
Sure.
So, hi everyone, I'm Lynn Clark and I make code cartoons. And I also work at Mozilla. I'm a principal research engineer on the advanced development team. And I work closely with the developer technologies team, which Till here actually leads. And we work on WebAssembly and the Rust to WebAssembly toolchain and Rust. And so we'll be talking about a lot of those things today. So first off, we'll start with what is WebAssembly? WebAssembly is a way of running programming languages other than JavaScript on the web. So up until now, to run code on a web page, the only language that you could use was JavaScript. But now there's WebAssembly, so this means that you can use other languages, like C or C++ or Rust. And since I started talking about WebAssembly, and that was about 2 years ago when WebAssembly was turned on by default in browsers, I've noticed that some people have this misconception about WebAssembly. They think that the MVP that landed in browsers back then, 2 years ago, they think that WebAssembly is the final version of WebAssembly. And I can understand where this misconception comes from, because the WebAssembly community group is really committed to backwards compatibility. So that means that the WebAssembly that you write today will continue to work far into the future. But that doesn't mean that this version of WebAssembly is feature complete. And in fact, that's far from the case. Features are coming to WebAssembly which will fundamentally alter what you can do with WebAssembly. I think of these future features kind of like the skill tree in a video game. We've fully filled in the top few of these skills, But there's still this whole skill tree underneath to unlock if we want to unlock all of these applications. So let's take a look at what's been filled in already, and then we can see what's yet to come. So WebAssembly's story starts with mscripted. And this made it possible to bring large C and C++ code bases for things like video games or applications, desktop applications, to the web. It did this by transpiling that code to JavaScript. And at first that JavaScript was slow. Then a Firefox engineer, somebody that was working on our JavaScript engine, saw how you could make optimizations to make this run really fast in the JS engine. And that gave us Asm.js. And once other browsers saw how fast you could make JavaScript go with Asm.js, they started adding the same optimizations to their engines as well. But that wasn't the end of the story. That was just the beginning of the story. Engines could still make this faster, but they couldn't do it in JavaScript itself. Instead, they needed a new language, one that was specifically designed to be compiled to, and that was WebAssembly. So what skills were needed for the MVP, for this running C and C++ on the web? Well, WebAssembly's designers knew that they wanted something that could support languages besides just C and C++. So they needed a language-agnostic compile target. So something that's like the assembly languages that you compile your desktop applications to. But this assembly language wouldn't be for an actual physical machine. Instead, it would be for a conceptual machine. And that compile target had to run very fast to meet users' expectations for smooth interactions and gameplay. And it also needed to load fast, because the web's users are used to pretty fast load times. But the kinds of applications that you run on a desktop are usually pretty large code bases, which means that there's a lot to download and compile when the user first goes to a URL. So we need this compile target to be compact. That way it can go over the network more quickly. Now these languages also needed to use JavaScript in a way that was different, you needed to use memory in a way that's different from the way that JavaScript uses it. They needed to be able to directly manage their memory. And this is because languages like C and C++ have a low-level feature called pointers. And pointers need to be able to read and write from specific memory addresses. But you can't have a program that you downloaded off the web just randomly accessing parts of your memory, willy-nilly poking around in your memory. So in order to provide a way to access memory like a native program is used to, but keep the browser secure, we had to create something that allowed us to give access to a very specific part of memory and nothing else. So to do this, WebAssembly uses a linear memory model. And this is implemented using typed arrays. So this is basically an array, just like a JavaScript array, except that that array only contains bytes of memory. So when you're accessing it, you're just using indexes into the array. But you can treat those as if they are memory addresses. And that means that you can pretend that the array is C++ memory. So with all of those things in place, you could run desktop applications and games in your browser as if they were running natively on your machine. And that was pretty much it for the skill set that WebAssembly had when it was released as an MVP. It was truly an MVP, a minimum viable product. It allowed certain kinds of applications to work, but there's still a whole host of others to unlock. So the next achievement to unlock is heavier weight desktop applications. Can you imagine if something like Photoshop were running in your browser? If you could instantaneously load it on any device just like you do with Gmail? We've already started seeing different applications like this coming to WebAssembly. So for example, the AutoCAD team has made their CAD software available in the browser using WebAssembly, and Adobe has made Lightroom available through using WebAssembly as well. But there are still a few features that we need to make sure that all of these applications, even the heaviest of heavyweight applications, run well in the browser. So first is support for multi-threading. Modern day computers have multiple cores that can process things in parallel. But to make use of these cores, you need support for threading. And there's another bit of modern hardware that processes things in parallel, and that's SIMD, single instruction multiple data. With SIMD, it's possible to take a chunk of memory and split it up across different execution units, which are kind of like cores. And then you can have the same bit of code, the same instruction, running across all of these different execution units, but each running on their own bit of data. Another hardware capability is 64-bit addressing. So memory addresses are just numbers. And that means that if your memory addresses are only 32 bits long, you only have so many memory addresses, about 4 gigabytes of memory addresses. But most modern hardware supports 64-bit addressing, which gives you 16 exabytes of memory address space. And that's a pretty big difference. So adding 64-bit support will take this artificial limitation on address space out of WebAssembly. But these applications don't just need to run fast, they also need to load fast. So one big step here is to do streaming compilation. This is where you're compiling as the file is being downloaded. And WebAssembly was designed for this. A tiered compiler also helps. So in Firefox, we have 2 compilers. The first one, the baseline compiler, starts when the download starts to give you that fast load time. And then another compiler, the optimizing compiler, runs on several threads in the background. And this one takes longer to compile the code, but it generates extremely fast code. We're also working on a new optimizing compiler called CraneLift, and that's designed to compile the code quickly, kind of like our baseline compiler, but because it can compile code in parallel at a function-by-function level. But the code it generates is actually still very fast, and we're currently working to see if we can make it faster than our optimizing compiler, our current optimizing compiler. But there's an even better trick that we can use to skip compiling most of the time. Unlike JavaScript, if you load the same WebAssembly file twice, it compiles to the same machine code. So we can store the compiled code in the HTTP cache. And when the page is loading and it goes to fetch the WASM file, the cache will give it that pre-compiled machine code. So this skips compiling completely. And there are even more ways that we can skip more work. So stay tuned to see what else happens in this space. Where are we with supporting these heavyweight applications right now? Well, for threading, we have a proposal that's pretty much done, but a key piece of that, shared array buffers, had to be turned off in browsers last year. They will be turned on again soon, though. SIMD is under active development at the moment. For WASM 64, we have a good picture of how this is going to work, and that's pretty similar to how x86 or ARM got support for 64-bit addressing. For streaming compilation, Firefox added streaming compilation last year, and in Firefox, that's actually so fast that it's actually, the engine's basically done compiling by the time you've downloaded the file. And other browsers have been adding this as well. We also added our baseline compiler last year, and other browsers have been adding the same kind of architecture. In Firefox, HTTP caching, did that land recently? It's very close to landing. And I think Chrome, V8 team, didn't you just land this?
Yeah, like 73 or something like that, or 74.
Congratulations. And other improvements are in discussion.
Oh no, I think we're currently rolling it out.
Oh, they're rolling it out now, okay.
Yeah, so 74.
Okay, so we'll be in 74 for the recording. So even though this is all still in progress, heavyweight applications are coming out today already, because WebAssembly already gives these applications the performance that they need. But once these features are all in place, that's going to be another achievement unlocked. And more of these heavyweight applications will come to the browser. But WebAssembly isn't just for desktop applications. It's also meant for regular small module style web development. Now, if you have a module that does a lot of heavy processing, that's a good use case for WebAssembly. And again, we're already seeing some of this. So for example, the parser in the source maps library that's used in Firefox DevTools and in Webpack, that's now 11 times faster after being rewritten in Rust compiled to WebAssembly. And the Gutenberg parser in WordPress is actually now 86 times faster on average. But for this kind of development to go mainstream, we need to have a few more things in place. So first, calls between JavaScript and WebAssembly need to be fast. When WebAssembly first came out, these calls were not fast because engines still needed to optimize them. And we finished our work on this in Firefox last summer. And now some of these calls are actually faster than non-inline JavaScript to JavaScript calls. That brings us to another thing though. You often need to pass data from your JavaScript function to your WebAssembly function. You need to return data back from it. So you need to pass in arguments, get return values. This can be slow, and it can be difficult too. At the moment, WebAssembly only understands numbers, and that means that you can't put more complex values like objects in as parameters. So you need to convert that object into numbers, put it into linear memory, and then pass something that's basically a pointer over to the function, and it pulls the data out of linear memory. That's kind of complicated, and it takes some time to convert the data into linear memory. So we need this to be easier, and we need it to be faster. We also need to integrate with ES modules. Right now, you can't use import and export with WASM modules. But that means that the WebAssembly module isn't really part of the JavaScript module graph. But just being able to import and export doesn't get us all the way there. We need ways to distribute and bundle WebAssembly modules. And since these modules shouldn't look any different to the people who are using them, there's no reason to create a whole separate ecosystem. And there's one more thing. Support for older versions of browsers, even those that don't know what WebAssembly is, like IE11. So where are we on all of this? Well, calls between JavaScript and WebAssembly are fast in Firefox now, and other browsers have been working on this as well. For easy and fast data exchange, there are a few proposals that will help with this, such as AnyRef, WebIDL bindings, and weak refs. And I unfortunately don't have time to go into detail on all of that. But in the meantime, the Rust ecosystem has created tools to handle this for Rust code. For ES module integration, the proposal is pretty far along, and Node actually just landed support, experimental support for it. For toolchain support, tools in the Rust ecosystem can package your code up to go on package managers like NPM, or registries like NPM. And the bundlers are also actively working on support. And finally, for backwards compatibility, there's the WASM2JS tool. So that takes a WASM file and spits out the equivalent JavaScript. And that JavaScript isn't going to be fast, but at least it will work in older versions of browsers. So once we unlock this achievement, we open the path to another two. Rewriting large parts of JavaScript frameworks in WebAssembly, and making it possible for statically typed compile to JS languages to compile to WebAssembly instead. So this is languages like Scala.js or Reason or Elm. For both of these use cases, WebAssembly needs to support some high-level language features. So first, let's look at rewriting parts of JavaScript frameworks. For a framework like React, you could parallelize the DOM diffing algorithm. And you could also speed things up by allocating memory a little bit differently. But you still need to interact with JavaScript objects, things like the user's components from that code. You can't just rewrite everything so that it uses linear memory, because that would be difficult and also inefficient. So you need to be able to integrate with the browser's GC at the same time. Now, this won't just help frameworks. This will also help languages that compile to JS like Scala, Reason, or Elm, because these languages use JavaScript's garbage collector when they compile to JS. And that's the same GC that WebAssembly running in the browser will be using. So they won't need to change their GC. We also need better support for handling exceptions. And we need good debugging support. You know, DevTools have made it easy to step through JavaScript running in the browser. We need that same support for WebAssembly. And finally, for many functional languages, you need to have support for something called tail calls. So where are we on all of this? Well, for garbage collection, our team already has a prototype of this working, but it'll still be a little bit of time before the proposals go through standardization. So we're probably looking at sometime next year. Exception handling is still in the research and development phase. For debugging, there's currently some support in browser DevTools, but it's not ideal. So there's a subgroup of the WebAssembly CG working on specifying that. And the tail calls proposal is also underway. Once those are all in place, we'll have unlocked JS frameworks and many compile to JS languages. So these are all achievements that we can unlock inside of the browser. But what about outside of the browser? Now, you may be confused when I talk about outside of the browser, because isn't the browser what you use to view the web And isn't that right in the name, WebAssembly? But the truth is technologies like HTML and CSS and JavaScript are only part of what makes the web. They're the visible part. They're what you use to build up user interfaces. So they are the most obvious part. But there's another really important part of the web which has properties that aren't as visible. And that's the link. The link's innovation is that I can link to your page without having to put it in some central registry or ask you or even know who you are. It's this ease of linking that enabled us to form global communities of people that we don't know. But there are two problems that we haven't addressed just having this link. The first one is, you go visit the site and it delivers some code to you. How does it know what kind of code it should be delivering to you? Because if you're running on a Mac, then you need a different machine code than if you're running on Windows. Does a website need a different version of the code for every possible device, every possible operating system? No. Instead, the site has one version of the code, the source code. And this is what's delivered to the user. And then it's translated to machine code on the user's device. The name for this concept is portability. With it, websites don't need to know what kind of device you're running. But that brings us to a second problem. If you don't know these people whose web pages you're downloading, how do you know what kind of code they're trying to deliver to you? It could be trying to take over your system, for all you know. Doesn't this vision of the web, where you're just downloading code from people and running it on your device, mean that you have to blindly trust anyone who's on the web? This is where the other key concept from the web comes in, and that's the security model. So basically, the browser takes the code and puts it in a sandbox. And it puts a couple of toys that aren't very dangerous into that sandbox with the code, but it leaves the dangerous things outside of the sandbox. So the utility of the link is based on these two things. Portability, being able to deliver the same code to any device and have it run, and the sandbox, the security model that allows you to run the code without putting your machine at risk. So what difference does it make if you think about the web in this way? Well, it changes how you think about WebAssembly. You can think about WebAssembly as just another tool in the browser's toolbox, which it is, but it's not just that. WebAssembly also gives you a way to take these other two capabilities of the web, the portability and the security model, and bring them to outside of the web use cases as well, these use cases that need them too. We can expand the web past the boundaries of the browser. Now you may be thinking, this already happened with Node.js. But as it is today, Node doesn't really get you there. It doesn't give us full portability, and it doesn't give us the same security, the same confidence to run untrusted code either. So with Node, it's possible to run JavaScript on servers and devices without a browser. So that does give us a bit of portability. But you still need native modules in a lot of cases, either because you have an existing C or C++ or Rust code base that you want to use, or because you need it to run really fast. But these native modules that you use to do that, they aren't portable. They have to be compiled specifically for that user's device. We're also still missing security here. Node could have chosen to take the same sandbox from the browser. It could have chosen to sandbox the JavaScript code. But Node made the design decision early on that JS modules would have full access to the system APIs. So JS modules can do things like read and write files on your machine. These capabilities, the things like full direct file access, those are the dangerous toys that aren't available in the browser sandbox. Even though these toys are dangerous, for the kinds of use cases that Node was built for, this kind of access does make a certain kind of sense. But the thing I want to make clear is that Node had a choice. They could have chosen for a sandbox-style approach with JS modules. But for native modules, Node actually really didn't have that much of a choice, because it's really hard to sandbox native code. Now, since Node has made this choice, that users shouldn't run untrusted code, if you're running a Node application on your computer today, you basically are saying, I trust the code that's in that application. Despite this design decision, WebAssembly can still help Node. It could eliminate most of the need for native modules, ones that are compiled specifically for the user's device, for that specific kind of device. And these can be written in WebAssembly instead and just compiled once. And these modules could then run across all devices just like JS modules. You wouldn't need to actually run Node.jip or have a whole bunch of binaries that need to be downloaded. The only problem here is that WebAssembly doesn't have direct access to the system's resources. We need to be able to pass in functions to WebAssembly so that it can work with the operating system. For Node, this would probably include a lot of functionality that's included in things like the C standard library and things that are part of POSIX, the Portable Operating System Interface, which is an older standard that helps with compatibility across Unix-like operating systems. So to make this happen, the Node folks would need to figure out exactly what APIs they want to give these functions. But wouldn't it be nice if that API was actually something standard, not something that was constrained just to Node, but that could be used across other runtimes and other use cases too? Now what I used to say here is a POSIX for WebAssembly, if you will, or a PWASIX, a Portable WebAssembly System Interface. And I would talk about how if this system interface were designed in the right way, you could even implement the same API, but for a different way on the web. So that's what I used to say here. But I don't talk about this in what-if terms anymore, because we recently started a subgroup of the WebAssembly community group to standardize this. And we seeded it with a proposal for how this system interface should work. So this new system interface is called WASI, the WebAssembly System Interface. Now WASI won't be part of the WebAssembly spec, and there will be WebAssembly hosts that don't make this system interface available, and that's fine. But for those platforms that could make use of the system interface, there will be a unified API for calling these functions no matter which platform your code runs on. And this would make universal modules, ones that run across both the web and Node, so much easier to write. So this new WASI standard opens up a whole bunch of new use cases for WebAssembly. And I'm going to let Till talk more about that.
Thanks, Lynn. So one thing that's really interesting here is since we announced WASI with Lynn's blog post at the end of March, there has been so much happening, and we've given versions of this talk before the announcement and also after the announcement, and it feels like every time there is something where we really would need to update the slides a bit. And we haven't fully done that, so I'll go over some of the use cases we are seeing, and I'll try to mention all the new things we're seeing that are happening since our announcement. So Lynn's right. WASI opens up use cases across many different domains, really very different domains. The first one I want to talk about is the domain of CDNs, serverless, and edge computing. And the Fastly CDN, we saw this on their announcement blog post of their Lucid engine on a slide earlier. They serve a significant fraction of the internet's traffic through websites like CNN or Reddit. And they are in a process of moving from serving just static files, which is what CDNs used to do, to running their customers' code on every single request. And a CDN is historically not meant to do that. So it's not meant to scale in that way. Serving a static file is very different from running an application. So they needed something that allows them to do that with incredibly small overhead while still being secure. And they are using this Lucid engine they announced to create new instances of a customer's code, serve a single request, and tear down the instance again with, they just announced this in a blog post, an overhead of in total, setting it up, tearing it down again, below 60 microseconds. And that allows them to go from serving static files to actually running dynamic code and providing much more functionality to their clients. So WebAssembly gives them the sandboxing that they need and the speed and the scale that they really need for this use case. People are working on building blockchain platforms with WebAssembly. By last count, we were up to 10 or so different ones. Probably last week a new one came out, I guess. There is interest in the IoT space, and this is also something where I think last week Intel announced their WebAssembly micro runtime, which is targeting really small embedded use cases and also the high security use cases for where you have an operating system that's embedded in your machine for high security parts, where then the overall machine is running something like Linux. And there are more projects that not only Intel but also players, other players in this space are working on. And there's lots of interest in writing portable CLI tools in WebAssembly. And WASI obviously gives the tools to do this in a safe way. And we've seen interest from companies building game engines where WebAssembly could be used as essentially an embedded scripting sandbox where you don't have to choose a single language, like in game engines that would often be Lua, and instead allow people to use whatever language that compiles to WebAssembly. And finally, with projects like Webassembly and Nebulate, some folks are trying to make WebAssembly run within operating system kernels. All of these use cases have in common that sandboxing and portability are really important for them, vitally important. But I want to highlight some additional important commonalities here. For example, how do things like file access work, or talking to the network? The way to do these things should ideally stay the same across all of these different use cases. If you use WebAssembly together with JavaScript, well, the JavaScript around it provides these pieces of functionality. You use fetch to load a file from a server. In a browser, this is all standardized, so you can rely on fetch working about the same in all browsers. You use Node's fs.read file to read a file. And you can also rely on this, but for a slightly different reason. There's really only one runtime you would use, and that is Node. Because Node is a de facto standard, you can rely on the APIs. You know the APIs you can use. Ideally, we'll have a similar situation with WebAssembly, where you know which APIs you can use and which will not be available. But we don't believe that this should happen through by the same way that it happens in Node, through one runtime being completely dominant. Instead, we're working towards a standardized runtime environment, which means there'll be a set of functions that you can rely on for things like file access or network access. This means that you can compile code once and run it in all of these different environments that we talked about, and in any runtime that provides these functions. Or also, importantly, in the browser. Because, as Lynn said, we want to bring things from in the browser to the outside world. We don't want to create a second way to use WebAssembly that is completely disconnected and just happens to use the sandboxing and portability in similar ways. We really believe these walls should be, well, torn down is maybe a bit dramatic, but at least perforated. And one important thing here is if you don't have a single dominant runtime, that enables us to have multiple runtimes where you're using a runtime that is really tailored towards exactly your use case, like the WebAssembly micro runtime that Intel just announced. That is a tiny piece of software that is really optimized for exactly this use case. And it wouldn't make sense to try to have a single runtime that targets that use case and also Fastly's use case and maybe writing CLI or eventually GUI applications for your desktop. So we really do not want to have and to need a one-size-fits-all solution. And for this standard library, we could say, let's just use POSIX and be done with it. But unfortunately, that eliminates one of WebAssembly's big advantages. The security model, in particular, the sandboxing. Lynn talked about how Node had a choice to make, at least for JS modules. A choice between keeping the sandbox that JS runs in the browser, or giving it an easy way to talk to the outside world. And we now have the same choice to make. Do we go with this easiest route, but give up on sandboxing, or do we do something different? Something that allows better control and leads to better security, and also auditability. That last point is really important. You should be able to see what an application can possibly do to your system, not by reading its code, not by looking exactly at what it actually is doing, but sort of what are the upper limits. You should be able to, I don't know, look at the tin, read the label and know this application can maximally do this. That seems fine to me, I can use it. But that is really incredibly hard. With POSIX, it is almost impossible to do in a really portable way. So there are solutions that exist for this, but they all work in different ways per operating system. So there goes your portability. And you don't want to be in a situation where you have to decide between security and portability. That sort of gets us back to square one. Unfortunately, solid portable sandboxing is incredibly hard. And back when Node was created, nobody had really figured out how to apply it to the real world instead of to systems that existed in academia. But with things like Google's Fuchsia operating system, this has changed. Better designs exist nowadays, and they are being proven to work in the real world. And for Wasm-Time, we are working on a standard library that'll make it easy to build secure, auditable, and portable modules and applications that'll work for all of these use cases. So that is sort of what I used to say, because by now I can also say it's not just us in Wasm-Time working on this, but it is all of us collaborating on the WASI initiative, on bringing this portable sandboxed system interface to WebAssembly. And there are multiple implementations in the browser, outside the browser, that all work and that allow you to take a single WASM file and run it in these different runtimes. And we know that WASI support is the #1 feature request for this for Intel's WebAssembly micro runtime, and they have expressed interest in supporting this because it makes sense. The idea of being able to take a WebAssembly file that was written by someone who didn't even have this embedded system in mind, and being able to actually run it on that embedded system, that is without it being precompiled, that is something new. But beyond the standardization effort, it's also important to make all of this usable, to make it usable in the tooling sense. So you shouldn't need to use highly proprietary tool chains where it's really hard to set them up. You should be able to use out-of-the-box C++ compilers or the Rust compiler toolchain. And debuggers, such as LLDB and GDB. And the IDEs using them under the hood, such as Xcode or Visual Studio Code. So as you can see, there is a lot of active development in this space, and we are all working hard to make it easy to target these use cases without having you as a developer targeting them, jump through hoops to develop and debug your code. And with this, we bring these capabilities of the web that Lynn mentioned, the portability and security, and the auditability that I mentioned, to all of these use cases.
Thank you, Joe. Let me turn this back on. Okay. Now let's zoom back out and look at the skill tree. I said at the beginning of the talk that people have a misconception about WebAssembly. This idea that the WebAssembly that landed in the MVP was the final version of WebAssembly. And I think you can see now why this is a misconception. Yes, the MVP opened up a lot of opportunities. It made it possible to bring a lot of desktop applications to the web. But we still have many use cases to unlock, from heavyweight desktop applications to small modules to JS frameworks, to all those things outside of the browser, like Node and serverless and the blockchain and portable CLI tools and the Internet of Things. So the WebAssembly that we have today is not the end of the story, because WebAssembly still has promise to keep and many places to go before it sleeps. I want to thank my collaborators on developing this talk, Luke Wagner and of course Till Schneidereit. And thank you all for listening. So perhaps, as I am also the next speaker, we should maybe do a little bit of Q&A so you can, take a little break from my voice for a little while.
Yeah, so thank you, Lynn. Thank you, Till. Do we have questions? Or who has questions?
Wait, we have another.
You mentioned that it was possible to cache the compiled form of WebAssembly, but it wasn't possible for JavaScript. What's the difference that makes this happen?
So with JavaScript, when you're running JavaScript, because it's not statically typed, you don't know the types when you are first compiling it. And so you actually need to watch what types are running through. And that, might not be the same 2 times that you run it.
Okay, got it. I've got a second one. When thinking of compiling to WebAssembly, most people think of C, C++, Rust, but you've also mentioned different languages. Like, how is the status on that? Like, I've heard that it's not that it wasn't really possible because garbage collection and stuff.
Yeah.
How's that working?
So some languages bring their own garbage collector with them. They actually compile the garbage collector to WebAssembly and bring that down with them. I think Go does that, right?
Go does that, yeah.
So languages like Go have WebAssembly support. The .NET platform has WebAssembly support. Swift recently, was that official or is that just like a Tinker project?
Tinker.
Okay, that's a Tinker project. But yeah, so we are seeing other languages, but it will definitely be, there will be a lot more languages that can target it as soon as GC interop is added.
There's also one additional piece that is really important here. Go bringing its own garbage collector doesn't mean that it has seamless integration with JavaScript and with the DOM. And by enabling WebAssembly, giving WebAssembly access to the same garbage collector as JavaScript and the DOM use, you can operate on actually the same objects, and that allows you to really seamlessly interact with the DOM, whereas for Go, the same divide exists as for these other languages.
On the skill graph, is there like some timeline to make these features official? Because you mentioned several times, okay, Firefox, I guess it's pretty far. I guess Chrome is probably far too, right? But I guess it's really officially supported if there's like a new version of the standard and browsers like have shipped that across the board. Is there like some kind of approx timeline for different
which
parts?
particular features are you interested in?
Or any?
So a lot of the stuff I was talking about, the proposals are pretty far along. So, but you can actually go and look at the proposals. There's a stage process. You can see where they are in the stage process. And then, like you said, Chrome and Firefox really are implementing things pretty quickly. I think Chrome might be ahead of us in SIMD, And we had some cool compiler stuff going for a while there that I got to write about. You know, but we are pretty much neck and neck a lot of the time. I think that Safari's tends to be a little bit behind. They have a smaller team, and they also tend to focus a lot. So they might be the one that is a little bit slower to implement. But
Let's say he is a little bit slower to implement.
yeah, the one person, yeah. But we're mostly keeping in step with each other, yeah.
Are there any plans to grant access to external devices like USB devices?
So, I don't actually know.
That should already be there because there's Web API for that, Web USB.
Right, yeah. But I mean, I thought, were you talking about through WASI or?
Yeah, for WASI, yeah.
Oh,
for Chrome, there's
sorry.
the USB.
Yeah, sure. There's a Web API for that. I think
Exactly,
it's
yeah.
origin
That's
built
that's
currently.
why I asked. Yeah.
Yeah, for WASI, are there any things you know?
So the most fundamental part in some ways of beyond the portability and security model, the most fundamental part of the WASI design is that it will be very modular, with the idea being that we can have quite a few modules being designed or the design being in flight at the same time. And to some degree, it actually depends on who pushes use cases and who pushes standardization through for use cases. And I guess we at Mozilla, for example, won't be focusing on USB access immediately. It also seems pretty hard to make that work in a safe and portable way. But for similar reasons as on the web. And so whether there will be official, standardized, published support anytime soon, I honestly don't know. I don't think anybody can know. But that doesn't mean that there won't be use case specific non-standard modules that you'll be able to use in production before they will be part of the official standard.
Thank you.
How about GPU support?
So I think that, are you talking about for WASI or Web GPU? For WASI, okay. Do you know if there's any?
No firm plans, but if there were a portable way to target GPUs similar to on the web, then that would be very attractive for WebAssembly, and Web GPU actually looks fairly attractive for that.
And how about sensors for IoT?
There are definitely going to be, so one of the things, you know what, we're getting to a lot of WASI questions, I'm realizing. I'm about to go talk about WASI. It might be better to save those questions for after the talk about WASI.
Okay, just to add, recently there has been a talk on Google I/O about Web GPU you might check out, which talks about progress on Web GPU. And it's not related to WebAssembly directly, but since there will be Web IDL bindings, it's pretty close already.
Yeah.
So, any more questions before we have a break?
First of all, thanks for the awesome talk.
Thank you.
My question is regarding AnyRef. So with the AnyRef proposal, WebAssembly cannot look into what is the content of the AnyRef object, right?
Mm-hmm.
Is there any other proposal that can be, manipulated by WebAssembly, the content of this object, like foreign object?
That is the GC proposal, or in some ways also web IDL bindings, depending on which ways to manipulate it you're talking about. But I think the GC proposal is closer to that. That'll enable access and mutation of a subset of our JavaScript objects, specifically typed objects.
Mm-hmm.
And so typed objects are a sort of sibling proposal to WebAssembly's GC proposal. There's the JavaScript typed objects proposal, and that will enable you to define objects that have a specified memory layout and allow JavaScript engines to very efficiently access these slots, this memory, because it is in exactly a predictable place, and will allow WebAssembly code to very efficiently access this. Whereas normal JavaScript objects are these very dynamic trees of data, data with pointers between them, and where it's really hard to predict where exactly the data is you actually want to have. That doesn't work well for WebAssembly. So generic support for just accessing JS objects won't make much sense, let's say. But typed objects will make a lot of sense and will enable you to use the same objects as JavaScript objects and as WebAssembly objects in a very native feeling way.
Okay. Thank you.
So maybe let's have a short break, because we will have another talk from Lynn, and afterwards, if we still have time, we will have a Q&A session. So 10 minutes.